Okay, so I'm going to start off with number 2, part D. So in class, I also put out in the recording session where I went through most of 1 and 2, but I didn't get to part D for some of my classes. So I'm going to pick up number 2, part D, and then we can finish this and go to number 3. Okay, so number 2, part D reads, at time t equals 0, particle Q is at location -90. Using the results from part B and the function velocity of Q from part C, approximate the distance between particle P and particle Q. So the big idea here is that particle P and particle Q, they both are starting at different locations and they have different velocities. So we're going to have to keep track of both their progress separately. And the way that we're going to keep track of their progress is using this formula, rearranging our first theorem, which is final position equals initial plus displacement. So if I start off with particle Q, I want to know particle Q's location at 2.8. I'm going to start off at x of 0 because that is the information that they provide for us. They tell us that at time t equals 0, particle Q is at -90. So I know I have a starting location to begin with, and I just want to know how much progress does particle Q make in that time period. So I'm going to take the integral of velocity. This gives me displacement. So this can go directly into our calculator because we have a formula that we can enter in. So -90 for x of 0. So he's starting at -90, and he's going to make progress of 135, a distance of 135. And then we add that together, and that means particle Q is going to end up at position 45.9. Right, moving on to particle P, let's figure out the location that particle P is sitting at 2.8. So particle P is also starting at x of 0, and then we're also going to find the progress that particle P makes in that time period. But the way that we gather information is a little bit different. Well, x of 0 is still given to us, but they say particle P is at the origin at time t equals 0. So we know x of 0 is going to be 0. But the progress that he makes, we are going to rely on the approximation. They don't give us a formula, but they do give us a table of values, and they say to use the approximation that we gathered from part B, using the result from part B. So part B, we're able to use trapezoid approximation to get that value to be 40.75. So we'll take that approximation, and that's the progress that particle P makes in that time interval, 40.75. So then that means particle P is going to start at position 0. He's going to travel to the right 40.75 units. He's going to end up at 40.75 on the x-axis. And finally, we just want to know what is the difference in location between these two particles. If we subtract those two distances or those two values, we can find the distance between them. So at t equals 2.8, the distance is 5.188 meters. Okay, any questions there? Right, no questions, number 1 or 2? All right, here's question 3. All right, a continuous function is defined on the closed interval from -6 to 5. The figure shows a portion of graph F consisting of 2 line segments and a quarter circle. Centered at 0.53. It is known that 3 minus root 5 is on the graph of F. So part A says, if the definite integral from -6 to 5 is equal to 7, find the value of the definite integral from -6 to -2. Okay. Okay, a little glitch there. I think I'm back though. Okay, I'll find the value from -6 to -2. Okay, so let me set that out here. -6 to 5, let's start off with this. We know that integral from -6 to 5 spans across all this region here. We want to know the integral from -6 to -2. So we have a portion of the graph that's not shown to us. Okay, but I'm going to split this up in a way that allows me to separate the part that I'm looking for. So I'm looking for -6 to -2. And then the remaining region is from -2 to 5. Okay, so we're able to create an equation that we know to be true. We're just taking a large region and splitting them up into parts that will allow us to locate the missing portion that we're looking for at the end. Okay, so we know what this piece is. This piece is 7. This is unknown, and so our job is to figure out what is the integral from -2 to 5. Basically, the region that we see in front of us here. Oh, sorry, -2 to 5. So all this that we see in front of us. So I'm going to highlight what we're going to be dealing with here. We're just looking at the region between the graph and the x-axis. Okay, so these are all geometric shapes or regions created out of geometric shapes. So triangle here, triangle here, triangle here, triangle here, and then this region, we can think of it as a square minus a quarter circle, right? If I take a square and if I subtract out that quarter circle, then I'm left with this region. So even though this is not a geometric shape, we're able to subtract 2 known geometric shapes to get this region there. Okay, so let me try to highlight some of these values here. 1/2 base times height. We know this is 1/2. This is also, but this is -1/2. Okay, now this region here, this is 1/2 base times height, so 1/2 times -1. So this region is -1/4. All right, this triangle here, 1/2 base times height. My base is 1.5, So the space is 3/2 or 1.5. And the height is 3. Okay, so it's going to give me okay, 9/4. And then finally, this region here, we want to think of this as a square minus a quarter circle. Okay, so the square, I'm going to highlight here. 3 by 3, 9. And then this quarter circle here is just 1/4 pi radius squared. My radius is 3. So 9 minus 9/4 pi. Okay, so we know this piece is 7. This is the unknown. And from -2 to 5, I'm going to add all these values together. So 1/2 minus 1/2 is just going to cancel out. -1/4, 9/4, and then 9 minus 9/4 pi. This will give me 8/4, which is 2. 2 plus 9 is 11. So we have 7 is equal to the integral from -62 of f of x dx plus 11 minus 9 pi over 4. I want to solve for the definite integral from -6 to -2, so I'll just subtract the 11 and then add the 9 pi over 4. So that's the missing piece. That's out of our range, but we're able to still find this area because we know the full region and we know the shown region. And if we subtract those two, we can figure out the unknown region. Okay, any questions there? Part A. All right, part B. Evaluate the definite integral from 3 to 5 of 2f prime of x plus 4. The thing we have to recognize here is these are two separate problems. So I want to separate this into the integral. I'll handle this separately away from the 4. They're both will both apply integral rules for respectively for their individual portions. But I like to kind of separate so that I don't get confused in terms of whether I handle one versus the other. So. And while I'm doing that, I'm also pushing coefficients out. Okay, so this one we can go through first theorem. This one we can go through power rule. f prime becomes f, and then we evaluate the bounds. And this one, we can go through power rule. 4 becomes 4x, and then we evaluate between 3 and 5. All right, so we want to find f of 5 and f of 3. Looks like that's provided for us in the problem, right? They tell us order pair 5, 3. They give us another order pair 3, which is 3 minus root 5. So we have our two f of 5 and f of 3 that we can pull from what's given to us.
Mr. Yang.
Oh wait, I'm sorry. My bad. This is at the 0.53. Okay, sorry. This 5.3 is talking about the quarter circle. My bad. So looks like we have to read the graph. The graph is 5.0. All right. Okay, order pair 5.0, and the other order pair is 3 and 3 minus root 5. Okay, let me try that again. F of 5 is 0. That's just based off of what we see in our graph.
You're saying, how do you figure out the ordered pairs without a calculator?
Oh, one of them is on the graph, and the other one is given to us here.
Okay.
So our answer is there'll be radical in our answer, but we don't have to get a decimal value. We can leave it unsimplified.
All right, thank you.
Okay, so this will take care of the antiderivative of my first portion. And then this here, this is 20 minus 15. Sorry, 20 minus, oh wait, my bad. 4 times 5, 4 times 3. 20 minus 12. Distribute 2 through the -3 plus root 5. So 2 times -3 is -6. 2 times positive root 5 is positive 2 root 5. And then I plugged in the 5 and the 3. So 4 times 5 is 20. 3 times 4 is 12. 20 minus 12 is 8. And then combine some like terms there. 8 minus 6 is 2. Okay, any questions with part B? All right, part C. The function g is given by g of x equals the definite integral from -2 to x. Find the absolute max on the interval. Okay, so we want to kind of understand the relationship here between g and f, which means that if I take the derivative of both sides, so basically our f of x graph is the g prime. So we're going to kind of reorient ourselves and understand that, okay, we're staring at the g prime graph here. All right, so find the absolute max. Before I do that, though, I'm going to gather my critical points. In this case, I'm looking for relative max. So I'll create my g prime sign line. So I'm looking for x-intercept because I know anything above the x-axis is positive slope. Anything below is negative slope. Anything on the x-axis is slope 0. So my critical points will come from my x-intercept, -1, and then this is at 1/2. Okay, let's just create our sign line based off of what we see here. Above the x-axis will translate to be positive slope. Below the x-axis, negative slope. And then above the x-axis, positive slope. I want to find the absolute max. So absolute max, I got to consider endpoints, and I have to consider relative max. We have a formula that, based off of this, can help us find absolute or any order pair of my g of x. So this is how I'm going to be testing all my points. Okay, g of -2. That's nice and easy because the bounds are the same. If the bounds are the same, it's just going to result in the 0. -1. Okay. -2 to -1, that's just going to be positive 1/2. And then from -2 to 5. I think we found that already, right? 11 minus 9π/4. Okay, so we want to find the absolute max. This is without a calculator, so we're just going to make some approximations here. I'm going to treat pi like 3. So general values here, 27 divided by 4. That's around 6 or 7, right? And the 11 minus 7 is going to be much higher than 1/2 or 0. So we don't have to know what this exact value is, but we do know that this is greater than 1/2, so this must be the absolute max. Okay, any questions so far? A through C? Okay, part D, find the limit. Now, whenever you see a limit problem that looks as complex as this, you may be tempted to jump into L'Hopital's rule because it looks like all these problems kind of have that L'Hopital's rule kind of leaning. But we have to make sure we confirm, right? We can't jump into that conclusion until we get 0 over 0. So we don't want to jump into that conclusion before we test it out. So I'm going to test 1 out to see what happens first. And again, arrows all over the place, right? We just don't want to deal with equal signs if we don't have to. All right, so 10 to the first power is 10. F prime of 1, that's asking about the slope of the F graph at 1. So the slope of the F graph at 1, if I just do rise over run, up 2 over 1, that's the slope of 2. F of 1 is just 1. Arctangent of 1. Okay, let's talk about this. Arctangent of 1 means when is tangent of theta equal to 1? That's basically what it's saying. Right? Arctangent, if you move that tangent over to the side, when is tangent equal to 1? Tangent is equal to 1 at pi over 4. The first instance when tangent is equal to 1 is at pi over 4. So this doesn't look like it's going to be L'Hopital's rule, right? Because we're not getting 0 over 0. So it looks like it's just this answer. There's no big procedure that we're going through here except understanding that this is asking for the slope and understanding how to get to arctangent of x, or when is arctangent equal to 1 at pi over 4. I guess you could clean this up in a way that doesn't have a complex fraction, but I will leave it like this. That's a numerically equivalent to a cleaned up answer, so we can stop there. So it kind of throws us off a little bit because we're expecting a 0 over 0, but it doesn't quite work out that way. But you know, if it's a real number, then we don't do anything with it. We just stop. Okay, any questions with number 3? Okay, number 4. All right, a cylindrical barrel with a diameter of 2 feet contains collected rainwater. The water drains through a valve at the bottom of the barrel. The rate of change of the height of the water with respect to time is modeled by dH/dt, where h is measured in feet and t is measured in seconds. Find the rate of change of the volume of water with respect to time t when the height of the water is 4 feet. So we know that this is related rates. Time is involved. We're trying to find dV dt. Gathering some information here when h is 4 feet. Okay, so we have our volume formula for our cylinder. They gave that to us. So I want us to visualize what's happening here. There is a valve at the bottom of the barrel. We know water is being drained out. So you can imagine that as water is draining, that h is going to be decreasing. But what about the radius? Is that radius going to be changing at all?
Would it stay the same because it's a cylinder?
That's right. It's a cylinder. It will stay the same. So that's something to be careful about. I know it looks a lot like the cone formula, but if you imagine that water level rising up or coming down, that radius is going to stay constant the whole way, which is going to make our process easier because this tells us that we don't have to hold on to r. R can just be replaced with a numeric value because it's going to stay the same value all the way through, and that'll simplify our calculus process. There's no need for product rule. There's no application of similar triangles. We can just replace that r with the number that's going to be the same all the way through. So here's my updated equation. V times 1 squared, pi times 1 squared h is going to be pi times h. Okay, we're trying to find dV dt. And let's see how far we can get. So V becomes dV dt. Pi stays, it's a coefficient, but h becomes 1 dH dt. And we have a formula for dH dt, which is this negative 1 over 10 root h. So I'm going to insert this into my dH dt and see if this h equals 4 can help me resolve this and get my answer down to a numeric value for dV dt. All right, I'm going to insert 4 in for h. Root 4 is just 2. Reduce that. 2 over 10 is 1/5. We're talking about change in volume over change in time, so cubic feet per second. All right, part B. when the height of the water is 3 feet, the rate of change of the height of water with respect to time, is it increasing or decreasing? Okay, so we saw this a little bit earlier. Well, the same concept coming up later. Came up earlier. Rate of change of height of the water with respect to time. We know that this statement is talking about dH/dt. But then all of a sudden, we gotta be careful. Anytime we see the word increase or decrease, it's changing. It's changing what we're dealing with here. So whenever you see increase, decrease, describing a rate, that means it's going to have to turn it into a rate below that rate. So it's basically saying we have to involve the second derivative. Okay, if the second derivative is positive, then we know dH/dt is increasing. If the second derivative is negative, we know dH/dt is decreasing. So we have to make our way to the second derivative, d2h over dt2. Okay, I'm going to do a little bit of cleanup, make it h to the 1/2. But we know our ultimate goal is to try to get to the second derivative. So we go through related rates here. We find the derivative of the outside, and then h's derivative we have to include as dH/dt. Keep the coefficient, go through power rule. And we just took h's derivative, so we need to attach dH/dt. It says when the height of the water is 3 feet. So we can insert 3 in for h. We can replace dH/dt with what's provided to us here. And we should be able to get all this down to a numeric value as well. I'm going to try to do a little bit of cleanup with that negative exponent here. And then dH/dt is just negative 1/10 root h. Okay, I'll replace all the h's with 3 and see what that gives me in terms of positive or negative for a second derivative. The root 3's cancel out, the 2 negatives become positive. 20 and 10 are both in the numerator, or sorry, in the denominator. I get 1 over 200. And that's a positive value. So therefore, the rate of change of height of water is increasing. Okay, questions with part B? All right, part C, at time t equals 0 seconds, the height of the water is 5 feet. Use separation and variable to find an expression. So this is solving a differential equation here. We're going to use this equation and solve for h. Okay, I want to set it up nice and clean. Fraction equals to fraction. I can do cross product to separate the variables. Here we don't have x's and y's, but we do have t involved. So that tells us that ultimately we're going to have h's grouping on the left. We want the t's on the right. We treat t's like independent variable, like x's. Right, but we still have some things out of place here. Give me 1 second. All right, so I want to move some things around. I would like to have the h's on the left, and I like to have this constant is okay on the left side, but I just like to have to keep that left side as minimal as possible. So I'm going to move the root h, move the 10 over, but I like to keep that negative where it is as well. So I'm just going to move the 10 over and then move the root h over. Okay, doing a couple of operations here at the same time. Okay, any questions there? Are we able to see where that separation is coming from? Okay, so this step is important. If you can't get to this step, you're not going to earn any other points on in this section, because everything is built off of a correct separation of variables. Okay. Now, if you mess up after this point, you can still earn partial credit over the course of the problem, but this is key here. If you don't have don't have correct separation of variables, it doesn't matter how correct your rest of the work is, you can't earn any points for this section. So this could be like 4 points that you can't earn anything on. All right, so separation of variables. I'm going to get this side cleaned up. I'm going to get this side cleaned up for power rule, get this side cleaned up for power rule. I'll bring that root h up. And we can jump into power rule from here. Add 1 to the exponent. Divided by that exponent. -1 over 10, we can go through power rule. Do a little bit of cleanup here. 1/2 in the denominator is same thing as 2 in the numerator. So I think at this point, I'm just going to go ahead and solve for C, get that out of the way. My order pair, 0, 5. Zero is my t value, 5 is my h value. So C is just going to be 2 root 5. Okay, so I'm going to go back to where I initially started making my substitution. And then piece by piece, I want to see, can I get h by itself So first thing I'm going to do is divide both sides by 2. Dividing by 2 is the same thing as multiplying by 1/2. So I'm just going to show I want to multiply 1/2 through. So this goes away, leaving me with just h to the 1/2. 1/2 times -1/10 is -1/20. 1/2 times 2√5. 2 goes away. I'm left with √5. Almost there. Square both sides, and we have h by itself. All right, questions with number 4. Number 5. Let R be the region enclosed by the graph g of x and h of x, y-axis, and the vertical lines. So we have x equals 0. We got x equals 2. Now, if you're looking at this going, wait, which graph is which? Maybe you're not familiar with the cosine of pi over 2x, but I think we can gain some hints about what this graph looks like. You see this is a quadratic, so you know that's a parabola, but there's a coefficient of -2x squared. So I know that I'm expecting this graph to look something like this, right? It's going to have to open down. So because of that, I know that the 6 minus 2 x minus 1 squared is going to have to refer to this portion here. Part A, find the area of R. So area is just going to be top minus bottom. Top function being the 6 minus 2, and then the bottom function being the cosine one. Oh, careful, when you do top minus bottom, you see how there are multiple terms within the bottom function? Make sure you protect that bottom function with a big set of parentheses. All right, this is going to feel tedious because this is non-calculator, so we got to go through all this work of working this out. So we got to do power rule, use substitution, right? You wish you could just enter this in the calculator, but this is number 5 here. This is non-calculator. Okay. Okay, there's a little bit of a shortcut in the sense that we can avoid having to expand all this out if we can just do a little bit of use substitution on the side. combine some like terms here. 6 plus 2 is 8. Okay, so we have 3 separate terms here. This power rule is pretty easy. This one is a little bit of U substitution. This is a little bit of U substitution. So I want to talk about how we can do U substitution without having to go through a whole setup of U substitution. We can save a little bit of time. Okay. So first things first, that 8 will become 8x. Now, if we go through U substitution, we can think of that x minus 1 as our U value. But if you just think about this as our U value without having to go through the whole U substitution notation, because you know x minus 1 is just going to produce a derivative of 1, meaning that there's not going to be any coefficient we got to keep track of. So just think of the parentheses as one variable. So think of it as 2u squared. We go through power rule, become u cubed over 3, and we immediately replace the u back in terms of x minus 1. So I'm just going to treat this like a power rule here. Parentheses cubed over 3. But I'm not going through a whole U substitution notation because there's not really any coefficient you got to keep track of. X minus 1's derivative is still just going to be 1. So I'm just jumping from here to here, just doing a quick power rule, knowing that this is going to be safe. And then a bit of a shortcut over here, there's also U substitution here. But we talked about before how if you go through U substitution for coefficients that are, or for expressions that are linear, you know that because your U value is pi over 2x, your derivative is just going to produce the reciprocal of it. So whatever my U value is, the only thing that's going to be left is going to be a coefficient of 2 over pi. And we can just go through we can just treat this like our U value, or imagine this is just an x without having to go through that whole process. We can save a little bit of time. Just understand that, okay, if my U value is pi over 2x, my coefficient is pi over 2, it's just going to produce a 2 over pi. So I just got to know that there's 2 over pi. That's going to be part of my my integral. Now, if you want to go through the full U substitution, you can. You just want to be able to save a little bit of time, especially in such a extended long problem here. Okay, so cosine's integral, it's going to be a positive sign. So this negative is not going to go anywhere. It'll stay as a negative. Coefficient of 2 over pi is going to be the result of that pi over 2x. Okay, so we were able to get to the antiderivative quickly, and then that's nice because now we can go into resolving our bounds from 0 to 2. Okay, upper bound first. Two in for x, 2 minus 1 is 1, 1 cubed is 1. So this is going to end up being sine of pi. Sine of pi is going to be 0, so that's going to wipe this out. But that's just the upper bound, right? We still got to worry about the lower bound. All right, careful with lower bound. Just because you see a 0 doesn't mean that it's automatically going to wipe everything out. So take the time to plug in. Don't just assume that every bound of 0 is going to cause everything to be 0. So it does for some terms, but not all of them. So 8 times 0, this does end up 0. If I plug in 0 in for x, I'm still left with a -1 cubed. -2 times -1/3 is going to be a positive 2/3. And sine of 0 is still going to be 0. Okay, so I think they do want to see you evaluate trig functions, but once you get into any of these regions, you can stop. You can stop either here or here or here. So it's up to you. But I don't think we can stop just at sine. I think they want to see that students can evaluate these trig functions. So you gotta go a little further than that, but once you're down to numeric values, then you can stop. Okay, a lot of work for part A there. Part B. Region R is the base of a solid. For each solid at each x of the cross section perpendicular to the x-axis, that's area A of x. So this is a cross-section problem, but this cross-section problem is a little different than what we're used to. But let's start with our formula. We know cross-section formula looks like this. Right. We know it's going to be some area that we have to insert, and that area is going to be based off of a base, and then that base we build our shape, right? Whether it's squares or rectangles or triangles or semicircles, and we have to go through that whole process. But here, they're giving the area to us, so we don't have to do any work. We just have to insert this area into here, and we don't have to do any base. We don't have to draw any figure out any formula for the shape. We can just make a direct substitution here. So it is cross-section, but it's also different in the sense that they've eliminated a lot of steps in the beginning here. But we do need to be able to see that connection and be able to understand that, you know, this goes in here. Okay. Same shaded region. So shaded region, our bounds is going to just be from 0 to 2. And if you look, this is just a problem that we can go through U substitution with a small U value with no coefficient that we got to keep track of. So we can do U substitution, or if you feel comfortable knowing that it's just natural log, you can jump into that natural log as well. Okay. 1 over u du, no coefficient. 1 over u becomes natural log absolute value of u. Do a little bit of cleanup, get it back in terms of x, and then we can safely work in those bounds. We get natural log of 5 minus natural log of 3. But you could also write this using quotient property and get it a little cleaned up, but either is fine. Okay, any questions with B? Okay, part C. Part C says, write but do not evaluate an integral expression that gives the volume of a solid generated when r is rotated about the horizontal line y equals 6. So here's y equals 6. Even though the axis is touching the shaded region, we know this is going to be a washer method. And we know that we're going to be drawing the radius perpendicular to our axis, so we know it's going to be top minus bottom as well. Okay, so here's our volume formula. Okay, we're going to create our two radius, one radius that extends from the axis to the furthest boundary, and the other radius that extends from the axis to the closer boundary. And so here's big radius. Here's little radius. Okay, big radius, 6 minus, this is our cosine curve here. Little r, 6 minus the top curve. All right, volume. Depth integral from one boundary to the next, from 0 to 2. And I'll leave my answer in one big mess. No need to clean anything up. We'll leave it like this. Okay, any questions? Washer method here. All right, final one, number 6. Okay, it says functions f, g, and h are twice differentiable functions, so these are all smooth curves, no sharp turns. G of 2 equals h of 2 equals 4. The line is tangent to both the graphs of g at x equals 2 and the graph of h at x equals 2. So tangent means that they must share the same slope. So part A says find h prime of 2. So even though we don't have an h of x function to find the derivative of, we do have the line. So basically, if we can figure out the slope of this line, we must also have the slope of the graph because they're telling us their slopes are equivalent. It's tangent. Okay, so they tell us that the slope of the line, or the equation of this line, we can just pull that slope by looking at the coefficient of our x. Slope is 2/3. So because the slope of the line is 2/3 and it's tangent to our curve, we know that h prime of 2 must also share the same slope, 2/3. Part B. A is given as 3x cubed times h of x, write an expression for a prime of x. So the way that this is set up, I'm thinking if I want to find the derivative, I have to involve product rule here. And then once I find a prime of x, then I can use that to find a prime of 2. So give me a second, guys. All right. Okay, we said product rule here. Okay, f prime g plus fg prime. Replace all the x's with 2. All right, h of 2, they tell us at the beginning that it's 4. H prime of 2, we just found that from part A, which is 2/3. So we just combine all this together here. All right, part C, they say that L'Hopital's rule does apply. So we know that this is going to result in 0 over 0. But we're going to have to go, we're about to go a little bit of backwards here to figure out f of 2 and f prime of 2. But at least we know what to do to get, or how the process will begin. We know L'Hopital's rule is part of this process, so we'll start and then see where to fill in the missing pieces here. Okay. All right, so I'm going to plug 2 in. Um, 4 minus 4 is 0. Now we don't know what we don't know what 1 minus f of 2 is. But we know that this must also be 0 because they're telling us that L'Hopital's rule applies. So we know that the condition for L'Hopital must be met. So because of that, we're kind of working backwards, right? We don't know what f of x is. We don't know what f of 2 is, but we know that it must be equal to 0. So working backwards, we can conclude that f of 2 must be equal to 1, right? That's the only way I can get this to work. So they're kind of giving us the end result, and we're going to have to kind of go backwards and figure out what must be true to make this end result work. All right, so we know f of 2 is equal to 1 just based off of the flow of this problem. But it's a little bit different because we kind of have to work backwards a little bit. So we know L'Hopital's rule applies. So we get 0 over 0. We're going to jump into our derivative. Okay. X squared becomes 2x. 4 becomes 0. Bottom part, 1 becomes 0. And there's a little bit of a chain rule here, right? Outside's derivative times inside's derivative. So outside is bracket cubed. So minus 3 bracket squared times the inside function's derivative, which is f prime of x. And then we fill the original bracket with the original f of x. Okay, now that we have our derivative, we're going to replace all the x's with 2. So we know what f of 2 is, but we're kind of stuck not knowing what f prime of 2 is. But let's see if we can find a way. So we're talking about function h. Right, we're talking about function h. They say that function h at the very beginning, it's a twice differentiable function. So h is continuous, right? So if h is continuous, that means the limit must be equal to the order pair. We know that our order pair of h of 2 is equal to 4, right? We know the order pair h of 2 is equal to 4. So if the order pair is at 2, 4, then the limit as h approaches 2 must also be equal to 4 because we know it's continuous, right? A limit, order pair, they must all be consistently the same. So even though we don't know the full, we don't know this portion of the limit, we do know that the end result is going to be 4. So that is how we're going to work backwards to figure out what f prime of 2 is within this expression. So if I cross multiply here, I can solve for, I can get that, eventually get that f prime of 2 by itself. The 4s can go away. Divide both sides by -3. So this is a little bit more challenging because it doesn't, it's using a familiar concept, but the way that we solve it is kind of unfamiliar. And we also have to have knowledge of the fact that even though they don't tell us, the limit must be equal to the order pair because they previously told us that h of x is continuous. So that's why we can set the limit equal to 4. All right, last part here, part D. Part D says, it is known that g of x is less than or equal to h of x for x between 1 and 3. Give me 1 second here. All right. It says, let k be a function satisfying g of x is that k is between g and h. If k is k continuous at x equals 2? Justify your answer. So let's go through continuity conditions. And also, the way that this is set up, we have information about the outer, but we're trying to prove something about the middle. So that indicates that there's a bit of a squeeze theorem here. So all squeeze theorem is if I can prove that the outer functions are equal to each other, that means the middle one must be equal. It's going to get squeezed between the two outer ones, and if the outer ones are the same, the middle one must also be the same. Okay, so if we step through continuity conditions here. Let's say since G and H are continuous, let me make sure that my full reasoning is good. Okay, so they're working backwards here. They're saying that because our function is continuous, we can go backwards and say that the limit must also be equivalent. So limit as x approaches 2. So this is going through a full process of showing that the limit is equal to the ordered pair, is equal to 4. And therefore, because of this, by squeeze theorem, the limit as x approaches 2 of k of x is also equal to 2. Sorry, it's also equal to k of 2, which is equal to 4. Okay, so basically in a nutshell, we just have to state that f of g of x is continuous, h of x is continuous. They both arrive at the same y value. So by squeeze theorem, k of x must also share all those properties that g and h share. All right, so we worked through all of 2019 FRQ. Do you guys have any questions?
Just on question 6, part A, you had y equals 4 plus 2/3 x minus 4/3. Where did that minus 4/3 come from?
Okay. Oh, I think I just distributed 2/3 through. But you didn't have to. So the only thing that I care about from part A was the slope. So that's my slope there. I did not do it. I just distributed 2/3 through to get that -4/3. But this is just part of, I can merge this together to get my y-intercept, but I didn't really need this value. Did that clear anything up for you?
Oh, yeah, thank you.
Okay.
Mr. Yang.
Yeah.
So I have a question that's kind of unrelated to the FRQs.
Mm-hmm.
So when you're doing like finding the antiderivative, when do you have to put the bounds in terms of the U substitution variable, or if that makes sense?
Right, right. Typically, if I'm going to use substitution, I tend to apply the process without the bounds. So let's say it was like u squared, and then I typically leave the bounds out of it. And then once I apply the antiderivative, I think typically the cleaner way, less messy way, is to bring that u back in terms of x, whatever that value is. And then I reintroduce the bounds from the original problem. I know I've been going, in the beginning, I would go through u substitution. You can go through u substitution or change your variable, make all your bounds the same. But I typically go through that so that students are able to see that how to change the bounds. So if you're forced to do it on the multiple choice question, you know how to change the bounds. You go back to the assigned value and you go through that process and get your bounds in terms of u. But typically, if I know I'm going to eventually bring things back in terms of x, I leave my my bounds empty, and I just know that after I convert everything back in terms of x, I can bring those x variables back.
So you only change the bounds when it asks for in terms of u, correct?
Right, right. I only change the bounds if they force me to have to use it, and they would sometimes force you to do it on multiple choice questions, where they would say, which of these answer choices is equivalent to this function, this expression? And a lot of them could have something like, you know, something like this, or something like, and you have to change the bounds in order to make it match the answer choice. It's not going as far as this, just stopping here and saying, if these bounds were filled in, what would they have to be?
Okay, that makes sense. Thank you.
Okay, good. All right. Anything else? All right, so I'll come back again on Teams at around 9, probably around 9:05, 9:10, and I'll just be available if you want to jump on, or over that course, over these next few hours, if you're coming across a problem that that you need some assistance with, I can provide that. So. All right, good luck with the rest of your studies. Maybe I'll see you tonight. If not, good luck tomorrow, and I'll see you Wednesday.
Thank you.
Thanks, guys.
Thank you.